Okay, that was just calculating gravitational forces. Okay, let's do something more fun with even more numbers and more directions. Let's do something more interesting. All right, because we look here, we're going to do calculating forces. We've done that. Now let's talk about local g, the difference between big G and little g. Okay, so what if you are near a planet? I believe we're all near a planet. This applies to all of us. This is like experiential and small compared to it. Right? Active learning. We're all doing the problem right now. There you go. So it will look something like this. Here's the big Earth here, like that. RE is here. RE, we'll use this a bunch, is 6.3 or 63,71,000 meters. Basically 6.37 million meters is the radius of the Earth. So I mean, we'll always give it to you, but that's a good one to kind of have in your head. And the mass of the Earth, we already said, is easy to remember, 6 times 10 to the 24. That's another good one. So there's the giant Earth sitting there happy. And the question is, where are you? You are pretty much always, within like the chalk line of this surface. Maybe you go camping and go to K2 or something or get in an airplane, but you're basically always right there. Right? You're always very close. So what that's going to tell us is we're going to say, okay, let's calculate exactly the force of the Earth on you, and it's equal to big G times the mass of the Earth times the mass of you, right, over r squared. But r squared, we said, is from the center to wherever you are. Okay? So if we think about it, that's really the sum. Then r is the sum of the radius of the Earth plus your height. How high are you? Okay? This is your height above the ground. Above ground. Now, what is the highest any of us have ever been? An airplane, right? 30,000 feet. You're now at 30,000 feet, right? I'm pretty sure none of us have been above 30,000 feet. Anybody work for SpaceX as a test dummy here? No. Okay. So in that case, if we turn 30,000 feet into meters, then the highest you've ever been is 9,000 meters. Okay. And what's the radius of the Earth again? 6,371,000 meters. So when we add, this is just like this problem. If you add, let's do it. R is 6,731,000. Oh, plus 9 is actually not so small. I think I'm going to put that in there. No, it's not. So if you add it, you're going to get 6,740,000. And are those very different? No. They're different to like 0.01%. It doesn't really matter. All right, so this plus 9,000. So it's whether the difference matters or not, whether you can drop it. Here it was 1/1,000,000th of this. Who cares? Here it's like maybe 1,000th or a 10,000th. Maybe it starts to matter if we're actually calculating something important or not. So let's leave it out. So the point is, we usually then write this way. We say the force of the Earth on you is big G times the mass of the Earth times the mass of you over, yes, it's actually radius of the Earth plus your height, but that, again, is small. Okay, here, I'll put approximately 0. In physics, we just say 0. In physics, we say pi equals 1. I mean, we don't really worry about actual values of things. So pi is 1, c is 1, it's all fine, g is 1. Okay, so we said that's about 0 because it's small. It's squared, of course, right? So then what we can say is if we simplify that, then it's equal to g m-e m-y over the radius of the Earth squared, because we're always at the radius of the Earth, basically. But let's rewrite it a little bit. We could say it's equal to g mass of the Earth over radius of the Earth squared times the mass of you. Right? So that kind of looks like your weight, right? F equals mg. F equals mass of you. And this is basically little g, right? The three terms together, g, big G, mass of the Earth, over radius squared, that is the acceleration near the surface of the Earth. Because you would find any little thing you drop over here, it's all going to look the same. It's all going to be F equals m little g equals ma. Everything's going to fall at this, at little g. So this is the acceleration that we learned about in the first part of the class near Earth. So what is it? Well, we plug in, and if you plug in 6.67 times 10 to the minus 11 times 6 times 10 to the 20 for the radius of the Earth, or no, let's see, the mass of the Earth, 6 times 10 to the 24 for the mass of the Earth, over that squared, you get 9.8. Right? So this is how we can measure 9.8, or if you know a lot about the Earth and how big it is, you can actually calculate 9.8. Okay? You'll never go high enough that it'll make a difference. If you go 9,000 meters in the air, calculate it again, it's 9.79 or something like that. Right? It goes down a teeny bit, not a huge amount. It's actually more affected by the geological structures under you. That can be a big deal. Do we have oil under us or do we have rock under us? G went down. Let's have oil under us. Let's start drilling. Right? So this is gravity, like scanning very sensitively the value of small g is one way they search for oil under the ground, because it would depend on exactly what's under you. Let's see. All right. So that is stuff about calculating the forces and how it relates to small g. So a big thing you'll see in homework problems, or some problems, is calculate small g somewhere else. What's small g on the moon? Well, guess what? It's about 1/6, because the mass of the moon is about 1/6 the mass of the Earth. Oh, then you also got to put in the radius of the moon. So you can put in different masses and radii of different planets and moons and asteroids and figure out what the local gravity is. Okay. What is the radius of the Earth? There are two values on the board. Oh, I don't know. I was doing it off the top of my head. I think it's 6,371. I think it's 6,731,000 meters. Pretty sure. We give it in every. Oh my God. Okay, we're gonna have to turn this off. They're gonna take my phone away. Why is small g not negative 9.8? Well, we were calculating the magnitude, right? So this is getting into this unit thing. Like, anytime I don't put a vector on it, it's a magnitude. So we calculated the magnitude of the force there, and we calculated the magnitude of g. We could do this whole thing, and I could say, let's do the actual force. This is the radial direction. So I could put an r hat on it, and then it would need a negative sign, and everybody would freak out. Right? So we're just doing the magnitude. Okay. We could do everything vector, but we're trying to just kind of get the basics down here. Okay. Okay. So that's how you calculate little g. Big G is a constant in the universe. 6.67 times 10 to the minus 11. It's the same everywhere in the universe. Maybe. We'll get to that in the next half. Little g is just the acceleration that it creates near a planet. Little g is different everywhere you go. Little g is one value here. It's actually a different value here. Right? The difference in those two is almost nothing, because the difference in those heights compared to the radius of the Earth is almost nothing. But little g varies. It's not a constant in the universe. Little g depends on your local situation, what planet you're near. That's the difference. They have different units and everything. Okay. The next thing is about orbits. So we're going to use this to do orbits. We'll do that. Let's take our break.